In this video presentation, we talk about the sixth experiment, titration of a weak acid with a strong base. If not clear from the title of this experiment, the objective of this experiment will definitely involve the technique of titration, which I know you're thinking, oh my gosh, another titration. Totally sucks to miss out on these good times. Thank you, COVID-19. So, continuing, we plan on using the technique of titration in this experiment to determine the acid dissociation constant, also known as the acid ionization constant, for an unknown weak acid. Then, making use of the information provided on the experiment handout, we'll use that measured acid dissociation constant to compare it to literature values in hopes of determining the identity of that unknown weak acid. This, by the way, is the second of the two unknown experiments you'll encounter this semester. So, some background information. As we would have learned, a weak acid, which we can represent as HA, will ionize in water to form the hydronium ion, H3O+, and the conjugate base, A- of that weak acid. And we can represent this ionization process with the chemical equation which now appears on the screen. A chemical equation you've undoubtedly seen no less than 1,000,000 times this semester already. We also recognize, just as we can write the chemical equation for the ionization of the acid, we can write an equilibrium constant expression from that chemical equation. Here, the equilibrium constant given by Ka, an acid ionization constant, equal to the concentration of hydronium and the conjugate base divided by the weak acid concentration. An expression that we will further manipulate using my favorite function, logarithm. I'm a big fan of the logarithm. Anyhow, by taking the negative log of both sides of the equilibrium constant expression and then rearranging, we obtain what I prefer to call the buffer equation because I have a hard time enunciating Henderson-Hasselbalch equation. Good grief. Here, the pH is equal to the pKa plus the logarithm ratio of conjugate base to weak acid, an expression that we could use whenever we have a buffer. Recognize at the midpoint of a titration, that is the halfway point of a titration, the concentration of the weak acid and the conjugate base are the same. They're equal. And the ratio of these concentrations therefore becomes 1, where we all know the logarithm 1 is 0, which means at the midpoint of a titration, the pH we might measure is the pKa of the weak acid. And it's the basis for this experiment. We're going to perform a titration and monitor pH during the course of that titration, measuring at some point the pH at the midpoint, allowing us to determine the pKa of the weak acid. So let's talk about the experimental approach. There'll be two parts to this experiment. In the first part of the experiment, we'll find ourselves monitoring pH while performing a titration, using a setup much as you see on the screen right now. There is, of course, the classic 50 ml burette, which you're quite familiar with, attached to a ring stand. Also attached to that ring stand is a pH probe, which as you can see is immersed into the same solution we're titrating with the titrant from that burette. All of which is on what's termed a stir plate. A stir plate is nothing more than a plate that contains a magnet. That spinning magnet will in turn spin a magnet which is in your solution. what we term a magnetic stir bar. Again, the stir plate spins the stir bar, which is in your solution, and that of course results in mixing. It's a great way to perform a titration. It's really quite simple. We're going to find ourselves recording the pH after the addition of an aliquot of our titrant. The volume of that aliquot, of course, depends on the region of the titration we're within. In the beginning, the aliquots are large. Towards the middle of the titration, that is, towards the equivalence point, we decrease the size of that aliquot to mere drops. Then, of course, afterwards, in the excess region, we increase the size of the aliquot to maybe as much as a half a milliliter. In any case, with the addition of each aliquot from the burette, we measure pH. And of course, given that it's a titration, you would expect to repeat this process. Aliquot, pH. And repeat. Aliquot, pH. And repeat. Aliquot, pH. Aliquot, pH. Aliquot, pH. Aliquot, pH. Aliquot, pH. Aliquot, pH. I think you get the idea. We'll be adding a whole lot of titrant and recording the pH over and over again. All of which represents the data we intend on recording into the notebook. Here's what the data might look like, with, of course, numerous measurements removed for the sake of the screen, which can only accommodate so much in terms of information. Here we have the titrant volume and the measured pH. From that titrant volume and pH, we can produce our titration curve. Again, the titration curve is your pH plotted versus the titrant volume. Note the characteristics shape, steep, shallow, which you would associate with a strong, weak. Here the pH increases because the titrant itself is a strong base. Let's review some of the points on the titration curve. You have the initial point, which represents that point in time before any titrant has been added. Just an acid in a flask waiting to be titrated, with a pH initially of 1.40. Soon after the titration begins, we produce a buffer, a mixture of both the weak acid and the conjugate base, a solution that resists pH change. Notice how in this instance this curve is relatively flat, illustrating that resistance. This is followed by the region in which we find the equivalence point. Note the equivalence point marked on this particular curve has a pH above 7, which of course is something you would expect. When you titrate a weak acid with a strong base, you expect a basic equivalence point. Note the volume of the equivalence point, 10 mils. Half of 10 is 5, and that 5 milliliters represents the midpoint volume. The pH at that midpoint volume is the pKa of the weak acid, and therefore the pKa for our weak acid is expected to be about 3.75. Because it wouldn't be fair to not have a complete presentation, I want to remind you that region which follows the equivalence point is the excess region, where the pH is determined predominantly by the amount of base, strong base, that has been added in excess. Continuing, once we've produced our titration curve, we'll perform the second part of the experiment, where we perform a second titration, this time with an indicator. We'll choose an indicator with a pKa that's plus or minus 1 of the pH at the equivalence point. We use the indicator because it provides an accurate determination of the equivalence point volume, which in turn allows for an accurate determination of the midpoint volume, from which again we obtain the pKa for the unknown weak acid. Referring to the last slide, the indicator we would want to use would have a pKa that's plus or minus 1 of the pH at the equivalence point, which is found to be about 9. Referring to the experiment handout, we would find that thiamyl blue, which has a pKa of 8.9, would be a great choice. The equivalence point in volume, according to the titration curve, was 10 milliliters. If we found the same volume for the indicator titration, we would celebrate, divide that value by 2 to obtain the midpoint volume. We would then refer to that titration curve to identify the pH at that midpoint volume, which as best as I can tell is about 3.8. Then we would celebrate and say to the world the pKa of a weak acid must also be 3.8. And referring to the experiment handout, identify the unknown acid as being formic acid with a pKa of 3.74. Thanks to COVID-19, we obviously won't be doing this experiment for real, but rather instead we'll be given data by our instructor. The instructor will provide you with data from which you'll do the following. You'll produce the titration curve, that is a plot of pH versus titrant volume. You'll predict the equivalence point in volume from which the midpoint volume is determined using data that's also provided to you by your instructor. You'll then estimate the pH at that midpoint volume on your titration curve, where that pH is of course the pKa for the unknown weak acid. You'll also calculate the concentration of the unknown weak acid using stoichiometry. Lastly, I would have you select an appropriate indicator for the titration. That, of course, you won't be doing. So sad. And because things are so sad and so dire, I've taken the time to found an awesome picture for you. That of a coffee bean drinking a cup of coffee, saying to you, "Cool beans." I know I have seen this image before. I know I'll see it again. Just as I always love saying, cool beans, good times. Enjoy!